In this lesson, we are going to create a smart LED that turns on in a dark room and off in a light room. We're going to describe the chemistry and physics that are governing photoresistors. Photoresistors, another name for that, is a light-dependent resistor. And then last but not least, we're going to utilize a voltage divider to read voltage in a circuit. This is going to be one of your biggest tricks in data collection in this class. So to begin with, I want you just to look at this setup that you see here. What's going to happen is this right here is my light-dependent resistor, or my photoresistor. And what's going to happen is if you cover it up, it's going to think it's in a dark room and my LED is going to light up. When I remove my finger, my LED goes away and it no longer is lit up. Dark room, it lights up. Light room, it doesn't. And so we're going to create this device together. How are we going to do that? Well, if you look back on my website, you will see the materials that are required. You will then see the image of the breadboard, and you want to make sure you set it up exactly like this. Now, it's a little hard in the picture to see what's connected to what, but this schematic does have a nano shown. So I think a schematic is sometimes more helpful because then you can see that, okay, my 5-volt wire goes directly into my LED, which you're able to see and on my breadboard itself. So notice 5 volt is here, and then that red wire takes it here to this leg of the photoresistor. Then from the photoresistor, we need to go to analog 0. So this white wire is taking us to analog 0, A0. But at that same connection, so all three of these are connected in the same row. This leg of the photoresistor, this white cable, and this resistor. And so the resistor now needs to go to ground, which you can see continuing on in this loop here. It's continuing to ground. But wait, there's more. So is there anything that goes from this leg not to ground? So because this one goes to ground here. This one now also goes to this resistor. And so that's where you see it on this loop, the resistor. And then the resistor goes to the negative leg of my LED. Then the positive goes here to D3. Which you can see that in the schematic. And so you want to make sure you have all of these connected. So what's literally happening is we are powering this photoresistor. It has a single line here that's going to take us to analog 0. Analog 0 is our input. That's going to be what's called our voltage divider. What a voltage divider is it's sort of like using this little plug right here. So if I unplug this wire, now I can take it and I can say, okay, tell me what the voltage is at this point here. And when I plug it in now, it's going to be able to read to my microprocessor what the voltage is at that point in my circuit diagram. So that's the important component here of this device. But then there's other things as well, and just making sure that at the same time as we are powering this photoresistor, this D3 is controlling the power to my LED. So it's going from D3 to the positive terminal of my LED to the negative terminal, resistor to ground, to ground, to ground. Okay? And so all of these components are important. So pause the video and set up your breadboard and your whole circuit just like you see in this picture or in this circuit diagram. Next, you're going to need to copy this code that you see here. You can just click on this little button and hit copy, or that's going to select it all. Press Control-C. Now come over here, open up a new sketch, select all that, and now paste in your code. And it's going to paste it correctly so that all of your syntax and all of your spacing is appropriate. Okay, so make sure you do that now. Next, you're going to want to compile your code and then download it to the device. Normally, if I see any errors, it's due to the microprocessor not being seated all the way into the breadboard or any of the components being loose. And so now, once you've finished uploading, go over to your device, put your finger on the photoresistor, and see if your LED lights up. If it doesn't light up, no worries. After we explain what's happening in the circuit, then we'll be able to troubleshoot and figure out how to best make your LED light up. So what's happening here? How are we able to, with our white cable, which we saw before, stick it in and measure the voltage? And then we're going to look at the code later and see, okay, well, why does measuring the voltage at that point allow us to turn our LED on and off? And we'll be able to look at the code and figure out why. But here is Kirchhoff's law. Remember that? Well, the idea behind Kirchhoff's law was that in a series, voltage is divided. And so what we have going on here is voltage which is our input voltage up here, which that's our 5 volts, which we're able to see right here with the red wire. It's going to my photoresistor. My photoresistor is basically a resistor, so that's going to be my top resistor. And then V out is going to be this white cable. We are measuring this white cable here and figuring out what is the voltage at this point right here. Well, since voltage is divided, you're going to have a voltage drop with each resistance. And so it's able to tell the voltage started out at 5, but then at this point, how much did it drop thanks to the resistor? Well, how much it drops is going to depend upon this resistor as well as the other resistor. If it's just one, you just have one, but you could also write 1R total for all of the bottom resistors, and you could sum it up by adding all of the resistors together. Okay, so all that stuff we learned before with series, parallel, still applies. Okay, but in this particular point now, we have an R bottom. So this one goes to ground, and ground goes directly to ground. So this resistor here is my resistance on the bottom. Or if we look at the schematic, we can see that. This photoresistor, this symbol here, this is the photoresistor symbol. And so the photoresistor is the first part. We start at 5 volts. We come to my photoresistor. That's our top. Come to this point here. That's where we can measure using our analog 0 input. We can measure what the voltage drop at that moment is, so our V out. And then we can come around here to our R bottom, 10 kiloohms, and then back to ground. And so what we're doing here is we're setting up a loop, and we got 2 loops going on, but we're setting up in this loop is where we're measuring our voltage drop here. Okay, we have another loop here going from D3 around to ground, and so it's important that you understand the voltage diagrams and what is happening within them. But what's awesome is by using this analog 0 as a voltage divider and setting it up in this way, we're able to measure data off of a device. And our device here is a photoresistor. So it is a detector of sorts, where it's saying based on the light that is being input, what is happening within the photodetector. And we're going to look at that in a minute. Our photoresistor is a cadmium sulfide photosensitive track that's laid out across some electrodes. And so the idea here is this cadmium sulfide is going to respond somehow to changes in light. Okay, then it's going to pass on those changes to an electrode surface, which is going to connect to your breadboard and basically allow those electrons to flow. But how the electrons flow is going to depend upon the light conditions around the photodetector. Why? What do I mean by that? And yeah, look up here at the top right-hand corner real quick. We have the United States symbol and the international symbol for a photoresistor. And so that's why you'll see on my schematics, I typically will use the USA symbol. But do notice how it's got arrows going in, which mean light comes in, the resistor, and then the circle is just like showing that it's a circle kind of environment. Typically, not always. Okay, but back to my question before. Why does changing light change this cadmium sulfide photosensitive track? What happens to it? Well, cadmium sulfide is a semiconductor. So if you remember back to your different chemistry classes that you've taken, you would know that a metal is a conductor. And so what happens in a metal is your conduction band and your valence band have overlap, which means electrons can travel freely through those two regions. With a semiconductor and with an insulator, you have a band gap. And so how big that band gap is going to tell you how easily electrons flow in that material. So in a semiconductor, electrons typically don't flow easily because we do have that separation. But when light hits the photoresistor, now electrons can leave their parent atom in the valence band, and it can jump up into the conduction band, now where it can move freely. And so in this situation, you have an increase in light, which causes a decrease in resistance, which means electrons can flow and you have increased current flow. So the idea here is as light increases, more electrons get promoted and you have decreased resistance. In darker conditions now, it's the opposite. Electrons are not able to travel up into that conduction band, and so you have increased resistance. And so this is the chemistry that's going to govern why a photoresistor works. Why cadmium sulfide? Well, cadmium sulfide is just one of many photoresistors that has been shown to be very sensitive across the entire visible spectrum. And so that's why we're using it in today's experiment. Okay, So which specific photo light dependent resistor am I using, and why is that going to matter? Well, I am, just for the sake of this experiment, I'm doing GL5539. If you see the colors on there, that is how I color coded my light dependent resistors, just so I could hand them out to students and they could give them back to me and I'd be able to know what their qualities were. And so I'm using this one, but I really want us to focus in on the light resistance and the dark resistance. Those are the spectral properties that are going to tell us a little bit about what's happening in our device and why. So let's look at those together. So here is the information for my circuit and for my photoresistor. So GL5539 has a resistance in the light of 75 kiloohms. I just kind of picked a number between the 50 and 100 on the parts list. And then in the dark, it has 5 mega ohm resistance. So you can see there's a huge difference here between the resistance in the light and the resistance in the dark. That is at this point, once again, in our voltage divider. So this is your R top and this is your R bottom. And so my voltage in is 5 volts. I have attached it to the 5 volts on my Arduino Nano. And then the resistor on the bottom that I am utilizing is a 10 kilo ohm resistor. So if we do the math here, my voltage in equals Vin out, Vn times resistance on the bottom divided by the sum of the resistances on the top and the bottom. So doing this, I'm getting these two values where you can tell for light conditions, we have a 0.59 volts at this moment. So you can tell the voltage has already dropped significantly across this area. But in dark conditions, wow, that voltage out is so tiny. That means there's a huge resistance, which it is. It's mega ohm resistance for my photoresistor. And so I can use this information to know that in the lighting conditions, I expect a small voltage, but not as small as the dark. So I have a huge difference here between the voltage input that I'm going to expect to see with my Arduino device for light conditions versus dark conditions. Now let's look at the Arduino code. We need to set up our code so that as the resistance of the photoresistor increases, meaning it's becoming darker, the LED now turns on. Because I mean, think about it. What good would it be to have your LED turn off in the dark? We want it to turn on in dark conditions. So let's look at that code together now. Here's our code. What is happening here? Well, first off, we're identifying our pins. And so this D3, this pin here is going to say that is the pin that's going to power my LED. So that is my digital 3. My sensor pin, I'm going to have that be my A0. And so that's where the input's going to be. Now, the thing I like about this code, I have taken code from this website that you see here and I have modified it. I modified it because in our next video, I want us to show you how to pull that data off and be able to graph it in Excel or a similar program. What I like about this is that we now have a calibration, okay? So any kind of sensor typically needs to be calibrated. So whether you're looking at spectroscopy where you've got a blanking a cuvette, or in this case where you're wanting to say, what's my initial condition? That way I can compare all future states to my current initial state, okay? Then we have little things in the code that are important. Set reading number 0. We are going to sample at a rate of once a second. So my delay is 1,000 between runs. So by setting my initial reading to 0, I'm making it so that reading number 1 is 1 second, reading 2 is 2 seconds. All right, what's next? So now we're going to set up the device. This is all things that are going to take place just for setup. So in setting up the device, we are going to look at my pin and notice it says pin mode LED pin. So if I come back up here, LED pin 3. So 3 is an output. I just defined that digital 3 is going to be used as an output, not an input. Then light cal, we are going to read sensor pin. So sensor pin is my A0. So it's saying read an initial voltage that's coming off of my device, and I'm going to store it as my light cal or my calibration initially. This serial begin 9600 is basically telling the instrument, if you will, that it's going to pretend to be an old school serial port. And so this is just confirming that the rate at which I'm sending information is equal to the rate at which the computer is going to receive it. And so that's just something that's going to be helpful in initializing the serial print function. What is the serial print functions? It's a way for us to take our data and store it as a CSV. So by storing it as a CSV, where we have reading number, which is how many seconds, so that's essentially going to be time, and then light value. What is my voltage value coming off? And so now it's got a comma in there, it's got spaces in there, and so that data is going to be collected as a comma delimited value, which we will look at in a future video. But all of that is just saying, hey, this is how we're going to talk to you, and this is what we're going to see. And now you're going to take readings. So instead of it being initial, it's the same sensor pin reading, but now each value is going to be stored and saved in that comma, space, comma, reading number, comma, light value setup. Okay. And so then my reading number is going to be incremented 1 with every single reading. And I once again still have my delay there of 1 second. Okay. But the important part now is down here. What this says is this is my calibration that I'm doing. So if you pressed your finger over your photosensor and you did not get your LED to light up, this is what you can play with. You may have to make it more sensitive or less sensitive. Remember, in our readings, we expected to go from 0.59 to 0.01. Well, when the Arduino reads these values in, it's going to read it as a part of a pin. And so it has a certain number, which we'll look at in our next video, of digits essentially. And the max voltage is going to be the high number and the low voltage is going to be the lowest value on that. And so what you're doing is you're saying, I'm expecting some difference in my reading, my output, or my input, excuse me, on A0. And so my light value, whenever I put my finger over my device, if it is not at least 50 different than my reading initially, then I will not get a change in condition. And so you can make it either more sensitive and make that number smaller, or less sensitive and make that number bigger. Okay. Then here comes the if-then statement. So if my light value is less than my light calibration, so if when I put my finger over it, that number went down, then you're going to turn the light bulb on. So remember, high means on. So I'm going to digitally write, I'm going to take number 3 and I'm going to apply power to it. So that's turning it off. But then whenever I let go and now my light value and my light calibration are almost identical, hey, what's going to happen then? I'm going to be low, which means I'm going to have my voltage supplied to my LED go away. It's going to turn my bulb off. All right, so that's the code, but what does this look like? Let me show you, and we'll cover more in this in depth in the next video. So here's my COM, my serial print. Okay, this is showing me my values. So once a second, I'm collecting a value. Right now, I don't have my finger over the photoresistor. When I put my finger over the photoresistor, notice how these values dropped dramatically. That's because my resistance is changing for my photoresistor. When I let go, you can see that it changes and it increases a lot. So we'll take this information and now we can graph it. And essentially, you now have created a device that will give you data for graphing. Let's look next at the serial plotter. So the one we just looked at was a serial monitor where we were able to get comma delimited data. But if we look at the serial plotter, it's going to look very similar. We're going to have some values and some readings. We put our finger over it, it changes. We let go, it increases. We put our finger over it, it goes down. So you can see how this is going to create some very pretty data, very pretty charts that are going to allow us to see the difference between a photoresistor in the light and a photoresistor in the dark. So what happened here? A0 is set to read the voltage from the photoresistor. When the photoresistor is covered, the resistance increases, but my value on my serial plotter went down. So if the reading is less than 50 as compared to the previous reading, the initial reading, that calibration reading, then the light is set to on, like you see here. But whenever the reading is less than 50 of the initial, so it's very similar to that initial calibration state, the light is set to low, which is the same as being off. And so with that, you have created an LED that turns on in a dark state and off in a light state. We've described the chemistry behind photoresistors, so the idea of the difference between the conduction band and the valence band, and how for cadmium sulfide, it changes based on the light conditions. And then we've also learned a little bit about how a voltage divider can be used to read the voltage at a point in a circuit.